So this is part 2, the method of Froebenius. The theorem of Froebenius says that if x naught is a regular singular point, which we learned about in our last video, of this second order differential equation, then there exists at least one power series solution in the following form. So the previous, when it was around an ordinary point, did not include this, x minus x naught to the r. So this is what's different. So we can combine these inside the series and just add the exponent since it's the same base. And r is some constant. So couple warnings. So the first warning is the theorem does not guarantee two solutions. It says it right here, there it exists at least one, maybe two. It doesn't say that, but that's what's understood. The second warning is that y is not guaranteed to be a power series. Even if we start off with this and plug it in, the first derivative and the second derivative, your solution could be such that it turns out not to be a power series. So that can happen. And r can be negative, a fraction, or complex, etc. So here's the idea, pretty much the same process as last section where we created a power series centered around an ordinary point. And here we're going to choose x naught is equal to 0. It's just easier to center it around 0, is a regular singular. So we have x to the r. Instead of x minus x naught, it's x minus 0 to the r. And we can bring that in to the series. The process is you take the first derivative and the second derivative and you plug it in. So same as the last section. Same process, except you have this n plus r power. You take the first derivative and the second derivative and plug in into the dE. And we do this in general, and we basically, from this process, we come up with a incidental equation, like a characteristic equation to find r. And it also does assume that we use p of x, little p of x is equal to x times big P of x, and little q of x is equal to x squared q of x. And then we get this indicial equation to solve for r. You can call it a characteristic equation if you like. And we get it by equating coefficients and setting n equals 0. It's not too hard to go through, but I'm going to skip that for today. So this is our characteristic equation. If we want, we can distribute it. And then these two, factor the r out. You get p naught minus 1. Maybe that's a little bit easier to memorize. So we can use this equation to find r and plug into, and then we'll be able to try to solve for the power series. Same process. It would be the same process as we did last time. And we do need to know that p naught is p of 0 above. That's because our x naught is 0 in this equation up here. And q naught is q of 0. And those are those formulas. And you should recognize those equations from the definition of regular singular. So not too surprising that we have to use those. Now there are also 3 cases that can happen with r. So yeah, and we can use either one. They're the same formula. So if the two roots are r1 and r2, and we do have to order them, r1 is greater than r2, then the one solution that is guaranteed is, and then the second solution depends on these cases. So when you subtract the 2 and it's not an integer, then it's pretty simple. y2 case 2. So in the case where, for example, they both are integers, And we should probably call this B because it's not going to be the first one we called A. Not going to be the same series. So I do need to point out C may equal to 0. So this would be the case where we could only get one power series. Case 3 is when they're equal. And so y2 would be y1, natural log of x. So let's do an example. So here's our DE, our second order DE. So we're going to rewrite this leading coefficient of 1. This actually does simplify. This becomes, and then that will cancel with that. So let's clean it up. So now we can see x equals 0 is singular. And if we want, we can check to see if it's regular singular. Little p of x is x big P of x, which is x. Again, this is p of x, and this is q of x. It's x times x minus 1 all over 2x. Those cancel. That looks like it's analytic. And that's clearly analytic. No problem points. We do need our incidental equation, and we're going to need p of 0. We can see here is, oh, I have this backwards. This is 1 minus x. Don't want to make that mistake. Did I factor correctly? So when I plug in 0, I actually get 1/2. For q of 0, you always get minus 1/2. So we're going to be using that for the incidental equation to solve for r. You can multiply by 2, see if it factors. Okay, so 1 is definitely bigger, so we'll start with that one. And we do have 1 minus 1/2 is equal to 1/2, which is not an integer, so this is case 1. So we'll start off using r equals 1, and then we'll have to go through and do this again for r equals negative 1/2. We'll get 2 power series solutions, it says. So y, so it's x to the r, a to the n, x to the n. So this one doesn't, just because we're taking the derivative, it doesn't always automatically start at 1. Because if you look at 1, we don't have a constant. So we are okay with starting this at 0. When I plug in 0, it's x to the 0. You have to have your constant. So we're good. We can start this one at 0. And then we have to take our second derivative and then plug it into our DE. So here, if I plug in 0 here, I'll have x to the 0 minus 1. That'll be x to the minus 1, which is 1 over x. Can't have that. So here we do have to start this at 1. So it's x to the 1 minus 1, which is x to the 0. That's where we want it to start, okay? So again, this one's a little bit harder. We have to be mindful of where it starts. It's going to be very important when we when we plug it into the function. It's going to be very important when we plug it into the DE. Okay, so now we're ready to plug this into the DE. And instead of plugging it into here, leading coefficient of 1, and plugging it in with fractions, it's going to be much easier to plug it into. It's going to be much easier to plug it into here. So let's do that. I'll copy this. And let's go ahead and replace y double prime and y prime and y into this equation. Here's y double prime. And I do want to distribute this. So we will be writing x y prime minus x squared y prime for that. So plus x y prime. Let's get that a of n there. You don't want to miss anything. and then minus y. It's right here. And that's equal to 0. So before we test anything, let's go ahead and bring in all of our x's into the series. So I'm going to add n minus 1 plus 2. It'll be x to the n plus 1. And this one is a 1, so that's n plus 1 as a power. And it's important to write your indexes. Okay. Now let's go ahead and test what powers each of these are. Plug in n equals 1 and I get x squared. Plug in n equals 0 and I get x squared. Oh, I'm sorry. I'm plugging in n equals 0 and I get x to the 1. I'm plugging in n equals 0, I get x squared. And I plug in n equals 0, I get x to the 1. So what we're going to have to do is pull out the first term here and the first term here, and we'll start with this second term. We'll start this one with n equals 1 and n equals 1. So we're going to pull out the first term from each so that they'll all be the same power. And then we'll worry about getting them to be the same index. So these two start at x to the 1, that's their first term, and the other two start at x squared, that's their first term. So we're going to pull one out of each of these, so we'll start the series at the second term, at x squared. So for n equals 0, I'm pulling that out. For n equals 0, it's a to the 0 times 1 times x to the 1. So I'm plugging it into here. A 0, 0 plus 1 is 1. 0 plus 1 is 1. And then my next term is n equals 1. And I do the same thing for this one. So I'm pulling out n equals 0. This is a minus a 0 times x to the 1. And then I'm at n equals 1. Okay. And if you see here, this minus this, it's going to cancel. And so let's go ahead and add our series back together. We basically have this plus this plus this plus this equals 0. So there's our equation, and we can triple check here. I plug in 1, I get x squared. I plug in 1, I get x squared. I plug in 0, I get x squared. I plug in 1, and I get x squared. Okay, so they're all the same power now. So now all we have to do is get them to be the same index or the same power. So we're going to switch it to k's. And what I want to do is I want to call this k for each one. K, K, K. So we have our equations. This one, I'm basically saying k equals, let me do it. Here I'm using k equals n plus 1, or basically if I solve for n, n equals k minus 1. This one, it's k equals n plus 1. It's the same formula. N equals k minus 1. This formula is k equals n plus 2, or n equals k minus 2. And this one is k equals n plus 1, or n equals k minus 1. Same formula. That's the other two. So we have to switch it everywhere for n. So here we want to switch it to k. So n equals 1. So k equals 2. N is k plus k minus 1. N is k minus 1. And then that'll be times k, x to the k. N equals 1, we plug it into there, we get k equals 2. We should get that for all the series. A to the k minus 1, k minus 1 plus 1, and then x to the k. This is a minus. This one's a little bit different. N equals 0, so I get k equals 2. We expect to get the same index, that's what we're doing. It's k minus 2 for n. K minus 2 plus 1 is k minus 1, x to the k. And this one, n equals 1, 2. Okay then, now we're ready to add them. They're all the same power, they're all the same index, we're good to go. So we do have x to the k in all of them. We'll factor that out. That 2 can be brought in. Can flip this order. Okay, so we have one series now. So equating coefficients, again, all the terms are 0. All of this is 0 too. So let's write that out. So that's just equating coefficients. And then looks like we have only one a to the k minus 2. All the others are a to the k minus 1. So we want to solve, let's get all the k minus 1s on one side, and we'll move the a to the k minus 2 to the other side, okay? So I'm factoring that out. So it's minus 1 plus k, and then 2k times k minus 1. Okay, and then let's just clean this up. And it looks like I left this term out. Let's go ahead and divide both sides. That's going to cancel. Okay, that cleaned up pretty good. For k equals 1. Well, that can't happen. Okay, there we go. So we'll let basically a naught be a naught, be the start. What we plug in, arbitrary constant. So 2 times 3 is 6, that's 1/7. 3a1. So we can plug in a1. That's 1/9. And then we plug in this. So what we have here is y equals, remember the series? We can cut and paste either one of them, but I'm going to copy this one. That's what y is. That's our series solution. So writing out the first 4 n equals 0, a naught. So we get a naught plus a1x plus a2x squared plus a3x to the third. That's n equals 1, n equals 2, n equals 3. So there's 4 terms. So y1, this is y1. x a1 up here, it's right here, 1/5 a naught so a1 is 1/5 a naught times x. A2 is right here, times x squared, and then A3 is right here, and it goes on forever. So y1, we can even, remember a naught was an arbitrary constant? You know, later on we'll just have our y equals c1, y1 plus c2, x2, but that's what that was. So we're gonna we can let a naught is equaling to 1, and then write it out that way. It looks nicer. x1 plus 1/5 x plus 1 over. Okay, and if you want, you can distribute that or not. So that's our first equation. And now our second equation. So remember, r was equal to minus 1/2. This will be fun. So we start off, and we'll use a second index. So here we have y equals okay. A little bit nastier to plug in, but it'll work. So there's our first and second derivatives and y. And we're going to plug it into the dE, this one. But I'll distribute that. Oh, and by the way, I forgot to mention this, but we don't know what's going on with the power. They're all fractional anyways, or so it seems right now. So they will all start at 0. Minus y is the first one. This one. And that's equal to 0. Let's bring those powers in. So I'm adding it. Okay, so now let's test where we're at. And these are all at 0. So we plug in, let's see the power. This is x to the minus 1/2. This is x to the minus 1/2. This is x to the positive 1/2. And x to the minus 1/2. Okay, so it looks like we can take out a term out of each of these, and then they'll be the same power, since that's the smaller one. If I take out n equals 0 from all of them, we'll start at n equals 1. They'll all be up to positive 1/2 power. Now, if you want, you could even try if you like, this is how I did in my notes, to go backwards here, start at n equals -1, which means you'd have to add it in the opposite. So that's a way to try it too, if you don't want to take 3 of them out. I'll just go ahead and take out one from each of those. Okay, so we're taking out n equals 0. So we take that out, and then let's take this one out. And then the next one will be of the same series. This one, I'm taking out n equals 0 also. And this one we're good, so we just copy this one. We don't need to take any of them out. And then here I need to take out n equals 0, and then we'll start at n equals 1. Okay, so we have 3/2 b naught x to the minus 1/2, and then so we can actually add all this together. We have 4, we have 2, 1. So all this combines, we have 4/2, 2 minus. Okay, so now they should all be at the same power. They're all half powers, I can see that. So now we need to get them to be the same index. So what we're gonna do is, this is the one that's different. So I want that to be the same power. So we're gonna, we want that power n plus 1/2 to equal to n minus 1/2. So since all of these are the same, except for this one, we're going to call this one k minus 1/2, and we're going to use k, just replace k with n with all of these. Except for this one. This is the one that needs to change. And so our formula is k minus 1/2 is equal to n plus 1/2. Cleaning it up, adding a half, or n equals k minus 1. Okay, so we're going to just change all of these 3. We're going to replace the n with k, and then on this one, we're going to replace n plus 1/2 with k minus 1/2, and then we'll have all the x's to the k minus 1/2 power. Should work. So this one, we replace n equals 0 right here, and it becomes k equals 1. B to the n to the k minus 1. K minus 1 minus 1/2 is k minus 3/2. X to the k minus 1/2, because it just gets replaced. And that's equal to 0. So now we have the same power, same index, we can add them. We will have this in common. So we have equals to 0, and we'll factor out that k minus 1/2. The series of 2 okay, and this is k equals 1 to infinity. And so now we do know that this, because this is equal to 0, is all equal to 0 by equating coefficients. And let's write that. So we'll bring this one to the other side, because it's the only one that's different. So what's left over here is all BKs. So I'm going to factor them out. BK okay, so we got that equation. Let's clean this up here. I'm going to distribute that. Oh, I'm off by a negative. This is, oh, right here, plus xy. And then if you notice, I'm going to do this. This becomes 2k minus 3, so those cancel. And there's our reiterative statement. So we'll start with b naught equals b naught, b1. Oh, wait a second. I think I say pattern. Yep, that works. So that's going to be 1 over 4 factorial, 2 to the 4th. I think that works. So our y2 so this is b to the n. We can basically set b naught equal to 1, arbitrary constant. And then cleaning this up, So remember, e to the x is x to the n over n factorial. So this is basically e to the x over 2. So our y, this is our y2, equals c naught y1 plus b naught y2. And that's it.